Greetings. In my previous videos, I managed to introduce the simple Rankine cycle and also the preheat Rankine cycle. In this video, I will try to introduce feed water heaters and especially open feed water heater, which are other additions to the simple Rankine cycle. They are called regenerative Rankine cycle, and what they do is to increase the temperature where the heat is added to the cycle and therefore hope to increase Carnot cycle efficiency and therefore the cycle efficiency. Well, let's see how this addition looks like in the TS diagram. If we draw a TS diagram, which I have already drawn for the Rankine cycle and also for the basic Rankine cycle. It looks like this, and I give the saturated liquid line a slope which is much sharper than its original slope, just to be able to demonstrate and show you what I want to do here. Now, in our previous example, there was a constant pressure line which was 10,000 kilopascals, and there was one constant pressure line which was the condenser pressure, and this one was 10 kilopascal. And there was one constant pressure line, which was this one, and this one was 4,000 kilopascal. And the original cycle, these were the two constant pressure lines, and our points were 1, and there was a point 2, and there was a point. This was the assume that this was point 3, and this was point 4. And we did all calculations for these points. And when we were introducing the reheat cycle, we also introduced 1.5, which 0.5 was in fact the intermediate pressure, where the first turbine delivers some vapor, and what we did in the reheat cycle was to reheat this steam to 800 degrees C and then expanded it again. Now, in this problem, we would do something different. What we would do is that we would extract some of this heat. We would extract some of this heat out and put it in contact with the liquid, which is already pumped to 4,000 kilopascals. So we have basically broken the pump work into two. Instead of one pump, we have two pumps. The first pump pumps water from point 1 to another point, which we would call it 9. We would call it 9.9. And then these two would come into contact, mix, and the ratio of the extracted steam is selected such that the outcome would end here, which is point 10. We call it point 10. And then we enter this saturated liquid into another pump and pump it to 10,000 kilopascals, and that would be point 11. So instead of heating from point 2 to point 3, we are now heating from point 11 to point 3. So the heat addition is done at a higher temperature, and what we expect is that the Carnot cycle efficiency would be higher, the equivalent Carnot cycle efficiency would be higher, and therefore the cycle efficiency would be higher. We understand that we have reduced power since the second turbine is not admitting as much steam as it did before, but we have gained some efficiency for the price of losing some work. And now I would do calculations for this new cycle. The first step for doing this is to draw the same cycle on the free body diagram and see what does it look like on a free body diagram. What have we already told you about this cycle? How would the instruments that are supposed to do that would be built and would be placed together to make this cycle? You see, this is a boiler. Assume that this is a boiler. This is our boiler. Assume that this is a boiler. And then the steam out of that boiler, the superheat steam out of that boiler, which is at point 3, enters the first turbine, which is also on the same shaft as the second turbine. So the two turbines are on the same shaft and they are running perhaps a generator. This is our combination of the turbines. Usually these turbines that run a generator are on the same shaft because they run at the same speed. They usually run at 3000 RPM or 3600 RPM. And the steam out of this turbine divides into two. One part goes to the second turbine, but one part comes in and goes to a basically open heat exchanger, and out of that open heat exchanger goes into another pump, and the outcome is fed into the boiler. Now, this is one entrance to the heat exchanger. This is a heat exchanger, which we call it open feed water heater. Open feed water heater. That's how we call it. But in fact, saturated vapor or saturated with vapor with some water droplets get out of the second turbine, enter a condenser, This is the condenser, and they are fed into a pump, and the pump outflow goes into the heat exchanger. So the heat exchanger has two entries. One from the first turbine, just like here. Heat exchanger has one entry from the first turbine, and the other entry is the exit from the first pump, which is here, point 9. The two mix, and the ratio is selected. The ratio here, you call it Y, which is the ratio. If the input mass to the turbine is 1, then Y would be the part of that 1, which would be the ratio of that 1, ratio per kilogram of steam entering the turbine that has been extracted to the heat exchanger and then fed into the second pump. So this one has the mass 1, but the mass here is 1 minus y, 1 minus y, and this is 1 minus y. So this part of our cycle experiences the mass 1 minus 1, but this part has the mass 1, this part has y, and then they join together to combine, and then the mass would be 1 into the second pump and then out. If we want to point to designate points to it, just like this one, this would be point 5, where it goes to the part of the flow goes to the second turbine. Out of the second turbine, it would be point 4 with the same properties. The properties don't change. The mass flow changes, but properties don't change. Out of the condenser, we have a point 1. Out of the first pump now, we have point 9. Out of the heat exchanger, we have point 10. And out of the second pump, we have point 11. And then the boiler delivers steam to point 3. So this is basically our cycle, both in a diagram and also in a TS diagram. Now, our first duty is to find properties. And what I have to do is to complete the table that we once produced for my previous example. We have many of the points we need here. We have many of the points we need here, 1, 2, 3, 4, 5, and point. We have added 3 points now. One is point 9, point 10, and point 11. These are the 4 points that we have added. Now, let's see if we can fill this table. How can we fill this table, the information in this table? And as for point 9, we know that the pressure is 4,000 kilopascal, 4,000 kilopascal. We do not know its temperature. We do not know its enthalpy. What we know is entropy, since its entropy is the same as point 1. And therefore, it is 0.6492. This would be the entropy of point 9. These two information are what we need to fill. As for point 10, it's on the saturated liquid line, and therefore, as we know the pressure, all properties are on the table, and we have just collected information about these points, point 4000 on the table, and now I'm able to just read this one. We know HF, we know T, we know enthalpies, HF, SF, we know all the knowledge, and we just uh, write it here. For point 10, the pressure is 4000 kilopascal, the temperature is 250.35, and enthalpy is HF, which is 1087.4, and the entropy is 2.7966. So for point 10, we have all the information as it's a point very easily readable from the tables. Now, for point 11, we know the pressure is 10,000. For point 11, we know the pressure is 10,000 kilopascal. We do not know the temperature, therefore we do not know the enthalpy, but still we know that entropy is the same as point 10, which would be 2.7966. And our next step should be to calculate values for points 9 and 11, which are in fact pump outlets. And we have already practiced once how to do it. Well, the first pump is an adiabatic and reversible pump, as we are assuming everything to be reversible in the cycle. Of course, if there are efficiencies, we know how to calculate them and add them to the cycle. But this would just make our calculation too lengthy for a simple video and wouldn't add much to our knowledge. So to calculate the first pump, we know that work of the first pump equals minus VDP minus V1 times P9 minus P1. This is the work of the first pump, and we know all the values. It is minus 0.00101 times 4000 minus 10, and the outcome is minus 4.03 kilojoule per kilogram. That is the work of the first pump. The work of the second pump, we are also able to calculate the work of pump 2 per kilogram of mass going through it is minus V10, as 10 is the entry point and specific volume doesn't change that much, times P11 minus P10, and we know all the values. Again, it is minus 0.001252 times 10,000 minus 4,000. And work for pump 2 would be minus 7.512 kilojoule per kilogram. And that's the work for the two pumps. Now, we could also use the first law for any of these two pumps and write down that H9 equals H1 minus pump work for the first pump, and this is negative, shall be multiplied by this negative, and therefore it would be 191 minus 4.03, and H9 would be 195.84 kilojoule per kilogram. As for H11, we should repeat the same practice, and it is H10 minus work for the second pump, and the numbers are 10, 87.4 minus 7.512, and the outcome equals 1094.9 kilojoule per kilogram. So now we have two further information for points 9 and 11. For point 9, H is 195.84, and for point 11, H is 1094.9. These are the two values, and if we go to saturated liquid line, for this enthalpy, we could read one temperature, which I read it to be 46.8 degrees centigrade, and for this one, 251.9 degrees centigrade. And you see the difference. You see in the simple cycle, the boiler had to start heating from the temperature 48.2 degrees centigrade. And now in this regenerative cycle, the boiler has to start heating from 251.9. So although we have lost some work in the second turbine, but still we have gained, we have in fact gained from the heat, from the reduced heat that we have to add to the boiler. Now, point 11 and point 2, although they look very close here, but still there is some 200 degrees difference between them, and that's a huge sum. So the next step for us is to calculate the ratio of mass that you have to extract from the second turbine, feed it into feedwater, open feedwater heater, and then mix it again with the water from the first pump. And this ratio has to be known, and for that we have to write the first law of thermodynamics for this feedwater heater. Now let's write down the first law of thermodynamics for this feedwater heater. It's a continuous operation, so left-hand side would be 0. The mass that enters from point 5 has mass y, so it is y times h5, plus the other mass that enters is from point 9. It has the mass 1 minus y, and its enthalpy is h9, and the mass that leaves is h10, and its mass is 1. In fact, it is per kilogram. All calculation are per kilogram of mass that enters the high pressure turbine. So the only unknown in this equation is y. So We insert values. 0 equals y times 3709.4 plus 1 minus y times 195.84 and minus 1084.4. Sorry, 1087.4. We do have all values in this equation, and therefore y would equal 0.254, which means that we have to extract 25% of the mass, which is quite a lot. We have to extract 25% of the mass from the turbine and feed it into an open feed water heater, just to be able to heat the liquid from the first pump. So let's see how much damage have we done to the turbine, how much reduction have we got from the turbine work. The turbine work in this case would be 1, the work of the first turbine. Its mass is 1, and it is 1 times H3 minus H5 plus the work of the second turbine, which its mass is 1 minus Y, and times H5 minus H4. And all we need to do is to put numbers here. Numbers are 4, 114.8 minus 3709.4 plus 1 minus y, y minus 0.254, and times 3709.4 minus 2347.8. And the outcome for work, turbine work, total turbine work of turbines is 1421.15 kilojoule per kilogram. And if we compare it with the work of the original cycle of the turbine of the original cycle, which expanded from 3 directly to 5, the work was compared with 1764 kilojoule per kilogram. We have lost some of the work since we have lost some of the mass entering the second turbine. Now, what has happened to heat? Heat added is H3 Q equals H3 minus H11, and that is 4114.8 minus 1094.9, and the outcome is 3019.9 kilojoule per kilogram, and that is a reduced heat for the boiler. Compare this value with the value we had to add for the original boiler, which was heating from point 2 to 3. For the boiler from 2 to 3, the heat we had to add, compare with G912.9 kilojoule per kilogram. Compare these two values together and these two values together, and you see that the heat added is also reduced, and it is from G912.9, it is reduced to 3019.9. So although we have uh, collected less work, but we have also um, done less heat, and that's important. How do we compare it? Well, we have to calculate the efficiency of the regeneration cycle. And the efficiency is the turbine work, which is 1421.5 minus the work of the first pump with a mass 1.y, which is 1 minus 0.254 times 4.03, which is the work of the first pump. Now the second pump has all the mass, so it would be minus 7.512. That would be the work of the second pump, and the added heat is 3019.9, and the outcome is 0.467 or 46.7%. This is the efficiency that we have got. Compare this value for the efficiency of 44.9%. Compare with 44.9%. So although we have got less work, although we have done less heat, but for the heat that we have added to the cycle, we have gained more work, and the cycle is more efficient since the Carnot cycle, the equivalent Carnot cycle for this cycle is more efficient. Open pit water heaters have other advantages as well. You see, since it's an open pit water heater, they are very good for aeration. It means that the air that has penetrated into the cycle, basically the condenser where the pressure is lower than ambient, would go through the cycle and would appear here. And here air would separate from the water, and pure water would enter the second pump, and the air would be flushed out. So there are other advantages to this heater as well. Many cycles have both reheats, open pit water heaters, and also closed pit water heaters. There are many of them, and the full calculation of them is far beyond the simple example. It's a project, and this is what is done in many other lectures, like power plants, and also many design offices for power plant usually do such calculations, and they are done with computers, softwares, and they produce the performance of different cycles. Well, thank you very much for watching, and cheers.